Hello everybody, welcome to another mini lecture on algebraic geometry. As you know, the defining feature of algebraic geometry is the close relationship between geometry on the one side and commutative algebra on the other side. And today we are going to continue talking about this relationship. Namely, we are going to see that there is an equivalence of categories on the one side we have the category of affine varieties, and on the other side we have the category of finitely generated reduced k-algebras. So let's write this down. We have the affine varieties on the one side. And we have the finitely generated k-algebras, reduced k-algebras. On the side of commutative algebra. So how does this equivalence work? Well, to say how it works, we of course need to talk about two aspects. One being the objects, and the other being the morphisms. I'm going to split this this talk into two parts. In this part you're seeing right now, we're going to talk about the objects, and in the next part we're going to talk about the morphisms. So let's say we have an affine variety V. Then we want to link V to a finitely generated reduced k-algebra. Well, what could we do? Let's just look at kV, which is the ring of regular functions on V, which is, since V is affine, the same as the coordinate ring k x1 to xn modulo the ideal generated by V. This is a fact you should already know by now, by the time you watch this video. If you would like to learn about this relationship for the first time, please have a look at the playlist Algebraic Geometry. So we have this this vector ring, but note that it is indeed of this type. So it is a finitely generated reduced k-algebra. First, it's a k-algebra since k, or the projections of k, to be precise, are in this ring, and it is finitely generated since x1 bar, xn bar, and so on. They are a generating set, a finite generating set, and it is reduced since I of y is a prime ideal. Since we assume that V is a variety, which means that V is irreducible, so I of y is is a prime ideal. And now what we need to ask is the following. Suppose we have an arbitrary finitely generated reduced k-algebra, which I will call R. Can we cook up a affine variety, let's call it V, such that this construction, this one here, gives an object that is isomorphic to R. So can we find a V such that k of W, I'm sorry, W. Can we cook up W such that k of W is isomorphic to R? Yeah, so what can we do? We know that R is finitely generated, so let's write down a finite set of generators, say R1 to Rn. And then we can also write down a surjective map from kx1 to xn to R. So this is a surjection. Namely, we just send xj to rj. Well, this is surjective, but it's obviously not injective in general. So if we want an isomorphism between we need to mod out by the kernels. So we have, by the first isomorphism theorem, kx1 xn modulo the kernel of this. Let's say this map is called phi. So modulo the kernel of phi. This is isomorphic to R. But in fact, we know that the kernel is an ideal, so let's write I instead. So we have this isomorphism, but we know something about R, namely we know it's reduced. And now this quotient is isomorphic to a reduced k-algebra, which means that this idea here, which is the kernel of phi, has to be a radical ideal. So the radical of I is the same as I. And well, then let's have a look at the vanishing set of this ideal, V of I, and then look at I of V of I. This is, since I, as we have just shown, as I is a radical ideal, as we have just shown, I of V of I is I. But this means that kx1 to xn modulo I of V of I is the same as k1 xn modulo I. But this one here, this is by definition this is the coordinate ring of this variety V of I. And now we have shown that this is the same as kx1 to xn divided by I. But we know that kx1 to xn divided by I is isomorphic to R. So we have found a variety. Oh, I have messed up notation again. This should be W. And here also. So we have found a variety W such that kx1 to xn divided by I is isomorphic to R, and this is what we wanted to show. And this establishes the connection in both directions. So we went from affine varieties to the side of commutative algebra, and now we saw that we can also go the other way. So for every finite degenerated reduced k-algebra, we can indeed find a variety W such that its coordinate ring is isomorphic to R. And now what remains to show is we need to show that this equivalence of categories also works on the level of morphisms. And this is what we are going to do in the next video. Thank you for watching. See you soon.